Most JEE aspirants lose marks here not because reactions are difficult but because they confuse the oxidizing agent. Watch this video, no more confusion. Hello students, let us start. Reagents for oxidation. First starting with oxidation of alkanes. KMnO₄, K2Cr2O7, anyone you can use. Alkanes here, no effect, no further reaction. Alkanes with tertiary hydrogen can form tertiary alcohol. Like you see, here it is tertiary carbon. So alkanes with tertiary hydrogen can form tertiary alcohol. As we know, it is tertiary carbon. Tertiary alcohol obtained. Next, CH4 plus O2 in presence of copper 523 Kelvin 1000 atm. Here methanol is formed. CH4 plus O2 giving CH3OH, that we will get here methanol. So methanol is formed. CH4 plus O2. If it is reacting in presence of molybdenum oxide, here methanol it is from aldehyde, it is methanol alcohol. When ethane react with burn in presence of oxygen, manganese acetate, oxidizing agent, it forms carboxylic acid, acetic acid. Very important reactions. Copper 523 Kelvin, 1000 atmosphere pressure, CH4O2 giving methanol, methyl alcohol, whereas molybdenum oxide giving formaldehyde, whereas manganese acetate giving acetic acid. Okay. Next, see oxidation of alkenes and alkynes per hydroxylation. Per hydroxylation, pink color of KMnO₄ disappears. If any substance giving this test, pink color of KMnO₄ disappear here. Per hydroxylation, that too especially which one? It is for KMnO₄, Bayer's reagent. See, I am taking here alkene, cold dilute 1% alkaline KMnO₄, which is Bayer's reagent, which adds OH2OH groups, 2 OH groups according to syn addition manner. So you will get syn diol or vicinal diol, and same side OH groups are added to the double bond. That is called as syn addition. Same side OH groups are added. See, whenever particular compound added to alkaline KMnO₄, the pink color of KMnO₄ disappear due to formation of your addition compound. Test for unsaturation. Even it is used as a test for unsaturation, you can specify here. Test for unsaturation. So in order to test unsaturation of the compound, you can use this. Next, osmium tetroxide or NaHSO3, syn addition occurs. Syn addition occurs. Here it forms again OH, syn diol, same side we are adding OH. Per acid, here anti-addition occurs. Per acid means one extra oxygen. Like carboxylic acid COOH, but here C₄OH, one extra oxygen. First here epoxidation occur, like ethylene oxide, cyclic ether, epoxide formation observed. Then further reaction with H₃O plus, bond breaks, and finally anti-addition of OH observed. Very important, anti-addition, syn addition, syn addition. So here anti-addition, so groups are opposite to each other. Or anti-addition meaning groups are added from opposite sides. Syn addition, same sides. Okay. Per acids are acetic acid like CH3COOH, but here per acetic acid 3 oxygen atoms. Per benzoic acid 3 oxygen atoms. Per formic acid 3. Metachloro per benzoic acid, metachloro per benzoic acid. Okay. Cis-alkene, when reacting with Bayer's reagent or osmium tetroxide, as we know both are showing syn addition. Cis-alkene undergoes syn addition to form meso compound. Cis-alkene undergo anti-addition in presence of per acid gives racemic mixture. For shortcut you can remember CSM, CAR. Trans-alkene syn addition gives racemic mixture TSR. T-trans S syn R is racemic mixture. Trans-alkene anti-addition meso compound TAM. CAR, TAM, any two if you remember, remaining combination automatically you will get. Okay. Now, see one question here. There is cis-alkene. How to identify it is cis? Here we know it is double bond, it is like this. It is cis. Groups are on same side. Right. So if it is cis-alkene, syn addition. Here see, Bayer's reagent gives syn addition. So if it is cis-alkene, syn addition, then it gives meso compound. That's what we wrote here, see, meso compound. So meso compounds are those which are having even plane of symmetry. Symmetrical, having plane of symmetry. Here you can see there is plane of symmetry, meso compound. Here also syn, so here also meso compound. Per acid anti-addition, here we know racemic mixture. both the enantiomers you will get, Da is enantiomer, Li enantiomer. So both are in equal amounts, racemic mixture, optically inactive mixture. Okay. Ozonolysis. Next, reductive ozonolysis, oxidative ozonolysis. Reagents are most important. Here anyway these are common in both the cases, O3 plus CCl4. CCl4 is solvent. Wherever there is zinc given, zinc H₂O, zinc, that is reductive ozonolysis. Dimethyl sulfide, triphenyl phosphine, all these are under reductive ozonolysis reagents. See, any one combination, different combinations I gave, 1, 2, 3, 4. Any one combination you can use under reductive ozonolysis. Oxidative ozonolysis, O3CCl4 common. Differentiating factors these, H₂O₂, H₂O, or oxidizing agent KMnO₄, K2Cr2O7 you can use. See example, here one alkene given, zinc O3CCl4 reductive ozonolysis. See, whenever reductive ozonolysis is given, simple trick here, use it. Break the double bond, add one oxygen on each side. Or you can show like this. Break the double bond, add one oxygen on each side. That's all. Trick it is. CH3CHO, you get CH3CHO. That's what we showed. HCHO or CH₂O. Both are same, HCHO or CH₂O. But for oxidative ozonolysis, so remember, for oxidative ozonolysis, what we do here, oxidative ozonolysis, here what we do, first anyway, both the products are same here, but further oxidation occurs. See, both the products are same, but further oxidative ozonolysis, further oxidation occurs, carboxylic acid, and here other same carbon having two OH groups, which is not stable. So here elimination of water molecule, remaining O2 you get, CO2 you will get. Okay. So here what we have to do, if it is oxidative ozonolysis, reductive ozonolysis, simple trick, break the double bond, one oxygen on each side. Oxidative ozonolysis, break the double bond. Here, see the carbon which is connected to double bond, this particular carbon, how many hydrogens here? Generally what we add? Generally we add one oxygen on each side. But oxidative ozonolysis, here how many hydrogens extra here? How many hydrogens extra? Here you can see one hydrogen extra. Add one more oxygen here, because one hydrogen here. See, once again listen here. For reductive ozonolysis, just break the bond, double bond, add one oxygen each side. For oxidative ozonolysis, one oxygen anyway we add, but here extra one more oxygen we are adding, because one hydrogen. For oxidative analysis, number of hydrogens you see here connected to double bond, same number of oxygens you have to add it. Here how many hydrogens? Two hydrogens, except other one, two more hydrogens we need to add here. Okay. Why we are adding 3 here? Once again I am showing. This you need to understand. Simple trick. No need to confuse. Just break the bond, 1 like above. But additionally here oxidative ozonolysis, as it is oxidative, extra oxygen atoms we need to add. How many oxygen atoms extra? You see the double bonded carbon, here one hydrogen present, so one oxygen, two hydrogens present, two oxygens added. So finally, this one is product. Here what you will get? No need to show in between whatever I showed here. These products no need to show. Direct product, final products only you have to write. Here what you will get? CH3COOH. That's what we got. Here what you will get? CH2, 3 oxygen atoms. See here. CH2, 3 oxygen atoms. So same carbon having two OH groups unstable. So here one water molecule you can eliminate and CO2 is formed. So final products here, carboxylic acid and CO2. Repeating the trick, if it is reductive ozonolysis, just add one oxygen on each side of the double bond. If it is oxidative ozonolysis, what you have to do? As usual, add one oxygen like reductive, but after that you count hydrogens, how many here? One hydrogen, one oxygen, two hydrogens, two oxygens. But if same carbon having two OH groups, eliminate water molecule, then CO2 you will get. Okay, final products are these. See once again. Here, Me2S, which is reductive ozonolysis. See, reductive ozonolysis. So what you have to do here? Break the double bond, oxygen, oxygen. Break the double bond, oxygen, oxygen. So here now you will get, after breaking, CH₂O, CH₂O. Middle, CO, CO, CHO, 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 CH3, CHO, CH3, CHO. That's all. Next, again reductive ozonolysis. See here there is. So what we have to do? Reductive ozonolysis, what we do simply, with respect to this reaction I am giving now, break the double bond, here one oxygen, here one oxygen. So finally here RCHO, RCOR we got. But if it is oxidative ozonolysis, don't forget, if it is oxidative ozonolysis, follow same trick. What is that? Here first you break the double bond, one oxygen, same like reduction. But now you see if any hydrogens present on carbon or not, double bonded carbon. Yes, there is one hydrogen, so one more oxygen I am adding. Add oxygen atoms equal to hydrogens connected to the double bonded carbon. Here any hydrogens? No. So as it is. So now what you will get product in oxidative ozonolysis? Here it is RCOOH, RCOOH, RCOOR, RCOR. That's all. Done. Simple reaction. Here we got. Next. Oxidative cleavage by KMnO₄, H plus or OH minus, meaning acidified KMnO₄, alkaline KMnO₄, and acidified potassium dichromate. Oxidative cleavage. So what we need to do, see here. Hot concentrated KMnO₄, H plus or OH minus, K2Cr2O7, H plus. Here also same. Simple here. What we need to do, here you break it. You break it here, actually carboxylic acid you will get. Whenever if you get RCH, carboxylic acid, if there is hydrogen connected to carbon, that is converted into carboxylic acid. See here one part. Other part anyway, here no hydrogen, so we write it as ketone. No hydrogen, we write it as ketone. See, if double bonded carbon having hydrogen, you convert this into COOH. If no hydrogen, leave it as ketone. Here also see now. Here we break the bond. Double bonded carbons having hydrogens here. Here also hydrogen, here also hydrogen. So what we do? Wherever there is hydrogen at double bonded carbon, those carbons we convert into carboxylic acid. Carboxylic acid. Okay, here also you see, where there is hydrogen, here there is hydrogen. So this particular carbon we convert into carboxylic acid, other one just add oxygen. Just add oxygen, CO. Here C. Now, here the double bonded carbon with hydrogen. Where is hydrogen? Here there is hydrogen. So double bonded carbon with hydrogen we convert into COOH. So this one, we are breaking the bond here. So other side is carboxylic acid, this one is carboxylic acid, remaining is CO. For other part oxygen only, just we are adding oxygen. Right here one simple, observe it. Double bonded carbon where there is hydrogen. Double bonded carbon where there is hydrogen forms COOH. That's what we observed in all cases. If there is double bond CH2, that is converted into CO2. Double bond CHR, that is converted into RCOOH. Double bond CRR, see double bond CRR where it is like this. Double bond CRR, which gives ketone. Double bond CHR like RCHR, carboxylic acid. That's what general information I wrote. Triple bond CH, CO2 you have to write. Triple bond CH, CO2. Remember the combinations. Oxidation of carbonyl compounds by using KMnO₄, K2Cr2O7. So here aldehyde in presence of acidified KMnO₄ gives carboxylic acid. Ketone in presence of KMnO₄ H plus, no reaction. But here whenever there is heat given, heat compulsory, whenever heat given, then only reaction occurs. See, if there is no heat, like for example if I show like this, if I show reaction without heat, like here KMnO₄ H plus, so here no effect. No effect, heat required here. Remember, without heat it will not show further reaction. In case of, see here all are symmetrical, right? Symmetrical ketones I mentioned. For example, see here. Here it is symmetrical ketone. But if it is unsymmetrical ketone given, unsymmetrical ketone, like different groups. See here, see. Ketone, right side is ethyl, left side is methyl. Unsymmetrical ketone is given, then you have to follow Popov's rule. Popov's rule meaning here, CO group remains with the smaller alkyl group. CO group remains with smaller alkyl group. See, smaller alkyl group is methyl, larger is ethyl. So CO group you need to show along with smaller alkyl group. So KMnO₄ H plus. So here you will get, anyway oxidation occurs. No doubt oxidation occurs. But here if they have given any isotopic form to represent isotope of the carbon, remember Here it goes with this particular part. Remaining CH3, CH2, COOH, further it is oxidized. It is oxidized. Okay, observe it. This particular part, here I showed, this entire part, carboxylic acid I showed here. These combinations, if you remember, easily can solve. By using tolerance reagent, ammonical silver nitrate is tolerance reagent. Aldehyde react with tolerance reagent. Tolerance reagent is that Ag plus coming from tolerance reagent. Aldehyde oxidized to RCOOH. Silvery grey mirror is formed. Silvery grey mirror is formed and inner walls of test tube, ammonia, H₂O. But HCHO, formaldehyde react with tolerance reagent and gives CO₂ gas. Silvery grey mirror not absorbed, CO₂ gas is absorbed. Next, failing solution, alkaline solution of Cu plus 2 plus tartarate ion. Alkaline solution of Cu plus 2 plus tartarate ion is failing solution. Like aldehyde, when react with failing reagent Cu plus 2 coming from failing solution, it converts aldehyde into carboxylic acid form, red PPT is formed. Here see, benzaldehyde, no reaction. Very important. Benzaldehyde will not show failings test or failings reaction. So benzaldehyde will not show reaction with failings reagent. So no reaction with failings reagent. Benedict solution, alkaline solution of Cu plus 2 citrate ion. This particular combination referred as Benedict solution. So again, aldehyde react with Benedict's reagent, gives carboxylic acid salt and cuprous oxide, which is red PPT. Next, Schiff's reagent. Schiff's reagent, for example, see here, it's a dye. Para-rosanidine hydrochloride, it's a dye. Para-rosanidine hydrochloride, when passed through SO2 gas, it becomes colorless solution. This colorless solution referred as Schiff's reagent. Schiff's reagent here formula given, it's not important, no need to remember. Just to remember Schiff's reagent. When NO2 react with aldehyde, here pink color of Schiff's reagent restored. Pink color of Schiff's reagent restored. See here, virgin here it is pink color. After passing SO2, it becomes colorless solution. This colorless solution of Schiff's reagent after passing through aldehyde, pink color is restored. If pink color restored, then it is aldehyde. Above all 5 tests, whatever we showed, 1, 2, 3, 4, 5, all these 5 tests. See here, whatever I showed ketone, under heating conditions it will give reaction. Otherwise, here no effect from ketone side. So above all these 5 tests given only by aldehydes and ketones will not give. Both ketones and aldehydes give 2,4-DNP test. 2,4-DNP test meaning 2,4-dinitrophenylhydrazine. Like you can say ketone I am taking or aldehyde you can take. Any one can give this test. 2,4-dinitrophenylhydrazine, which is Brady's reagent, which is also known as Brady's reagent. So Brady's reagent or Borch reagent, which is orange red in color. Whenever both are combined, here you will get 2,4-dinitrophenylhydrazone derivative. It is hydrazine, it is hydrazone, which is yellowish orange PPT. If yellowish orange PPT is absorbed, then given compound is either aldehyde or ketone. Baeyer-Villiger oxidation, oxidative cleavage of CC bond adjacent to a carbonyl which converts ketones to esters, cyclic ketones to lactones. Ketones to esters, cyclic ketones to lactones. Can be carried out in the presence of paracids or H₂O₂ and Lewis acid. Can be carried out in the presence of paracids or H₂O₂ and Lewis acids. What we are doing overall? Adjacent CC bond to carbonyl group which converts ketone into esters. Like see here, COO. Here before going to that, you see here now, migratory aptitude. See Baeyer-Villiger oxidation later in aldehydes and ketones chapters. Later in upcoming chapters, we are going to discuss mechanism of Baeyer-Villiger oxidation. Presently, just you remember the trick. Migratory aptitude, here group migrates during mechanism. Hydrogen having maximum migratory tendency, tertiary alkyl, secondary alkyl, aryl, primary alkyl, methyl. Migratory aptitude. Trick is here, just you have to insert oxygen. Where you have to insert oxygen? Insert oxygen between carbonyl carbon and the higher migratory aptitude group. See here now. Here insert oxygen between carbonyl carbon higher migratory aptitude group here. See what is present here? CH3 present, one ring present. CH3 lowest. CH3 is lowest, remaining all you can consider more than that. So you place oxygen between carbonyl carbon and more migratory aptitude group, that is, so here we placed oxygen per acid. Here you see ethyl and methyl. Ethyl having more migratory aptitude. If you compare with methyl, primary alkyl like ethyl also you can consider. So here where you have to place oxygen? Here you have to place oxygen between carbonyl group and higher migratory aptitude. Here we have to place oxygen. Cyclohexanone, it is symmetrical. Here you will get caprolactone. 6-member ring with CO here. O. Here is the 5 heterolytic compound. Heteroatom present oxygen. So inside the ring, one more extra oxygen came. Caprolactone. Important. Key point, aldehydes, Baeyer will get oxidation gives carboxylic acids. Not like this. Esters or cyclic lactones will not get. Here you will get carboxylic acids. See JEE Mains online 2024, 29 January, shift 1. Question. See first question here. From the compounds given below, number of compound which give failings, positive test. Just now we wrote above, aldehydes will give and benzaldehyde will not give, ketones will not give, above test. So here if you see, benzaldehyde, it will not give test. Acetaldehyde, yes, it gives test. Acetone, it is ketone, right? Acetone is ketone, so it will not give test. Acetophenone, acetophenone is also a type of ketone. Here it is acetophenone, which will not give test. Methanol, methanol is aldehyde, formaldehyde, which will give test. 4-nitrobenzaldehyde, 4-nitrobenzaldehyde, like here it is like this. We know benzaldehyde will not give, which will not give test. Cyclohexane carbaldehyde, so cyclohexane carbaldehyde is like this, which will give test. So how many total? Total we are getting 3 will give test positive, failing test. Ketones will not give, benzaldehyde derivative will not give, compound here in this nitrobenzaldehyde will not give. Okay, next. JEE Mains 2026 January shift 2 question. So see here, CH₄O₂, see different reaction, number of reactions which produce alcohol as the major product. They are asking reactions which produce alcohol as the major product. So now we need to check which products are obtained here in each case. So one by one you have to check here. First, MO2 molybdenum oxide produce formaldehyde. Here it will produce formaldehyde, so it's not alcohol. Manganese acetate. Manganese acetate produce acetic acid. It's not alcohol. Tertiary butyl. See tertiary hydrogen available here. Tertiary butyl group. So here what you will get, KMnO₄ reaction, tertiary butyl undergoes oxidation to produce tertiary butyl alcohol. Here you will get alcohol. CH3, C, tertiary butyl alcohol. So here what you will get, if we clearly show like this for better understanding, CH3, 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 CH3. Here alcohol we are getting. So C is presently correct. CH4 plus O2. So if it is copper reacting with that, it produces methanol. Here it produces methanol. Above already we wrote above all these reactions. These reactions above we wrote already just now. Yes, it is also correct. So presently C and D. CH3, C double bond CH, CH3, KMnO₄ H plus. KMnO₄ H plus produce vicinal diol, right? Just now we studied above, scene addition occurs. So here it forms CH3, OH, CHOH, then CH3. So vicinal diols formed here. Vicinal diols, KMnO₄ H plus. But here see, it's not alcohol, it's a diol, right? It is. Remember, it is diol. It's not like mono alcohol. It is not mono alcohol, it is diol it is. So they are asking Alcohol as a major product, only single alcohol we consider, mono alcohol we have to consider here. Diols we should not consider here. So here C and D correct answer here. So overall answer is C and D. C. I hope all the questions clear to everyone. These are most important organic reagents. Only part 1 we completed. Still we did not complete all the organic reagents. Part 1 of oxidation we completed. Next video we are going to discuss about part 2 of oxidation. After that, reduction reagents. Now only oxidation reagents. If you watch all these oxidation reagents parts, reduction reagent parts, with ease you can solve questions based on upcoming chapters. I hope all the questions clear to everyone. For more updates, follow the channel. Thank you. Thank you everyone.